Hello, everyone. My name is Maria Jose Jimenez, and this is my third lab for Physics 2211, finding the mass of a black hole. Today's objective for the lab include utilizing fundamental physics principles such as Newton's second law and Newton's universal law of gravitation to thereby determine the mass of a black hole. We will also be able to generate an understanding of the motion that occurs using GlowScript, utilizing the data from the interactions between the two bodies. Lastly, we will calculate the black hole's force, the star's position, and its mass. Some of the formulas that I used include Newton's second law, or the momentum principle, which states that the rate of change in momentum is equal to the sum of this rate in both parallel and normal direction to the system's velocity. The normal direction means a change in the direction of motion equal to the net force in the normal direction pointing to the center of the circle. The parallel component represents the magnitude of velocity equal to the parallel net force in this equation. We also use the velocity and position update formulas and the parallel and perpendicular components of dPdt and Fnet. Also, we use the equation force of gravity, which will be used for Newton's law of universal gravitation. This law states that the gravitational interactions between two objects is directly proportional to their respective masses and inversely proportional to the square of the distance separating them. G in this equation is the gravitational constant, which is 6.67 by 10 to the power of negative 11 in Newton's meter squared over kilogram squared. This was used to calculate the mass of the black hole. To do this, I set the gravitational force equal to the net force, which I obtained from the computational model. As for my initial conditions state that the system is a star whose mass is 2 times 10 to the 30th power. The surroundings are the black hole. We must remark that there are no other gravitational interactions that are present during this interaction. Also, the time step we'll be setting as is that of an Earth day, which is 86,400 seconds. Excuse me. With this, we will be able to calculate the mass of the black hole using the net force, star position, and star mass. And for my seed, I placed my Georgia Tech email. For my calculations, I use various equations that I previously mentioned before, such as P equals mv, Newton's second law, the momentum principle, and the fact that Fnet equals perpendicular plus parallel force, and that force of gravity equations, among other equations. On the right side of the slide, we can observe that we calculated the initial and final position vectors, the change in velocity, the change in momentum in order for us to be able to calculate dp/dt, and then we calculate net force through Newton's second law, and later on we calculated Fnet parallel and the perpendicular components. Lastly, to find the mass of the black hole, we use this force of gravity equation, which I found to be 1.29 times 10 to the power of 34 kilograms. And for my computational model, after I finished my code, this is what it looked like. The black hole is in the origin, and the yellow ball is the star that is representing it, and that will be like orbiting the black hole. The orange arrow will represent the net force factor, Fnet, and the blue arrow, the perpendicular component, and the pink arrow represents the parallel component. From my computational model, we can observe that the Fnet grows exponentially as the star approaches the black hole and decreases when it gets further away. We could reason this through Newton's universal law of gravitation, since as the distance decreases, the magnitude of the force increases exponentially, and as distance increases, the magnitude of the force decreases exponentially. What does this mean? How is net force different from rate of change in momentum? Well, first of all, net force is what will cause the change in momentum. Net force causes an acceleration, which then causes a change in velocity, which thereby causes a change in momentum. So, this does mean that they will be equal to each other numerically, but momentum is the consequence of net force. Lastly, we must ask ourselves, what if? What if instead of wanting to take a quick look at the black hole and leave, you decide that you want to enter it and orbit around the black hole? So the initial velocity of the spaceship would have to change in order to enter some kind of orbit around the black hole. The velocity to enter the orbit would most likely need to have like a smaller x component and a larger y component. And I found this out